Welcome back, everybody. We are going to be discussing the Hecke correspondences from the third of three very important perspectives today. That'll be the orbit space perspective. We've already discussed them from the Galois theoretic perspective and from the moduli perspective. So we'll look at them from the congruent subgroup perspective today, and then we'll introduce the diamond automorphisms, and we'll look at those from all three of the major perspectives as well. Okay, so first, the diamond notation. Remember that gamma sub 0 of n is the set of all matrices in SL2 that reduce to an upper triangular matrix mod n. So if D is in Z mod n Z cross, let's let diamond D be any element of gamma sub 0 of n with lower right entry equivalent to D mod n. That's it. Okay, what if I give you an integer D? Well, as long as its GCD with n is 1, then I can still talk about diamond of D, even though D isn't literally in Z mod n Z cross. Because I can just say, oh, well, diamond of D, that just means diamond of D mod n. Okay, because D mod n will live here because of this GCD condition. Okay, first of two theorems of the day. First is proposition 5. The following diagram commutes. So we've got our usual Hecke correspondence T sub p given a prime p from the complex points of x sub 0 of n to its divisor group. Okay, then I've got the usual isomorphism from all the way back in proposition 3 from the complex points of x sub 0 of n to the orbit space of the action of gamma sub 0 of n on H star, which is H union infinity and the rationals. So the extended upper half plane, if you like. We know this isomorphism induces an isomorphism on divisor groups. That's just always how it works with divisor groups. So the question is there a map on the bottom here that commutes this diagram? In other words, is there a way of thinking of the Hecke correspondence congruent subgroup or orbit theoretically? And the answer is yes. So here's what the map is. It will send the orbit of Z here to the following divisor. Now remember, a divisor of a group is a finite formal sum of elements in that group. So here's the finite formal sum that the orbit of Z goes to. It goes to the sum from b equals 0 to p minus 1 of the orbit of Z plus V over P plus the orbit of PZ if P doesn't divide n. And it goes to the exact same thing without the extra orbit of PZ formal point if P does divide n. Okay? So I don't know how intuitive you find this compared to the other two perspectives, but it's a good perspective to have because when we define Hecke operators, they'll look something similar to this, okay? So what does this look like for gamma sub 1 of n? This exact same statement holds if you replace x sub 0 of n by x sub 1 of n, gamma sub 0 of n by gamma sub 1 of n, of course. And how do you modify that bottom map, the bottom arrow? Well, you don't actually change the p divides n case at all. If p doesn't divide n, you change one thing. You change this last class here. This last orbit here will be replaced by the orbit of diamond of p times pz instead of just orbit of pz. So you add an extra diamond of p in there. Remember, so this is just a matrix times a, acting on a point in the upper half plane. So this makes perfect sense. It's another point in the upper half plane. I can certainly take its orbit. Okay, the proof of all this is in CSS chapter 3. So now this is a nice segue into the second major type of operator we want to look at when studying modular curves. The first was the Hecke operator. We haven't even actually defined those as operators yet. We're working on looking at that Hecke action as correspondences right now, but we will soon. The second type of automorphism slash action we want to look at is the diamond action, and we'll look at those as automorphisms first. So let's let E over Q adjoin J be an elliptic curve with J invariant J, like the universal elliptic curve, for example. Recall the Galois group of the n torsion extension of E is isomorphic to GL2 of Z mod NZ. We saw that a while ago. You can also identify the function field K of x sub 1 of n with the fixed field of, there's a lot of different things you could put here, but we can look at the function field K of x sub 1 of n as the fixed field of what we'll call H, which is the set of all matrices in GL2 of Z mod NZ with entries A, 0, C plus or minus 1. Where A is some unit in Z mod NZ cross, and C is just anything in Z mod NZ. You probably expected me to put like ones here, and you may have even been further shocked that the C isn't here. It's down here. But remember, there was a proposition a while ago that said, when we're looking at things from the function field perspective, we need to transpose. So that's why the C isn't up here. Okay, it's down here. So we're looking kind of at lower triangular matrices right now. And the point is, yeah, like, I don't really need to put 1 and 1 here. I can just pick any unit and put it here and then put plus or minus 1 here. There's a lot of different subgroups of GL2 of Z mod NZ that actually work. That's the point. Okay, so this is the one that we'll focus on. So x sub 1 of n is the fixed field of this subgroup of GL2 of Z mod NZ. Okay, now you can check pretty easily that H is normal in G, where G is the lower triangular subgroup. Okay, Okay, well, that means G mod H acts as a group of automorphisms of K by Galois theory, okay? But if it's a group of automorphisms of K, then it must be a group of automorphisms of X sub 1 of N. Now, why is that? This took me a minute to understand. So, I mean, you can naively just be like, oh, well, remember, I can recover a curve from its function field by the curve's field correspondence. True, but that doesn't really tell you how to think of G mod H specifically as a group of automorphisms on X sub 1 of N. So I think here's what you want to do. Here's the action. Just take a point that you want to act on in X sub 1 of N. Okay, write down a function in the function field K, having a simple pull at the point of interest, the point you want to act on. I can certainly apply the action of G mod H on K, and this function that I've written down with the simple pull, that's in K. So I can act on it with this group of automorphisms. Okay, when you do that, you get a new function, right? That's what actions do. And you just look and see, where does this new function that I get as a result of the action, where does that have a simple pull? Whatever point that is, that'll be another point in X sub 1 of N. And that's how G mod H acts on X sub 1 of N. It takes the point of interest, use it as a simple pull of a function, acts on the function, looks at where the new function has a simple pull. Okay, now you can take this group of automorphisms G mod H, and you can actually identify it with Z mod NZ cross mod plus or minus the identity. Here's the isomorphism. You just take a coset A0CD plus H, and you send it to D, the lower right entry. You send it to its coset right here. So you send it to D plus the set plus or minus I. And remember, okay, so G mod H, that's a group of automorphisms on X sub 1 of N. You can think of it that way. I'm going to let diamond of D be the automorphism of X sub 1 of N corresponding to the coset of D in Z mod NZ cross mod plus or minus I, right? So I'm going to pick some D here. I'm going to look at its coset here. Then I'm going to look under this isomorphism here at the corresponding coset in G mod H, A0CD plus H. Whatever that is, that's going to be my diamond automorphism, diamond of D. Okay. And I mean, it's amazing to me that this is even well defined. Like, it doesn't matter which matrix you pick that has a lower right entry D, but it works. Okay. So that's how you think of the diamond operators Galois theoretically. How do you think of them moduli theoretically? You should expect a pretty clean perspective from the moduli through the moduli lens, because when we were looking at the Hecke correspondence, I think the cleanest of the three perspectives so far was the moduli theoretic perspective. Let's see how the diamond operators look moduli theoretically. All right, so we're going to look at the second major result of today, proposition 6. This is going to tell us how to think of the diamond automorphism, not just Galois theoretically, but actually moduli theoretically. So let's let E over Q adjoin J be an elliptic curve with J invariant J. Again, just think universal elliptic curve if you like. Let S be a subset of the complex projective line containing all places of bad reduction. For E, all the usual stuff, fix an ordered Z mod NZ basis for the n torsion of E. Let P be its second element because we're transposing. Then for all D in Z mod NZ cross, it turns out the following diagram commutes. Okay, the diamond automorphism can be viewed as an automorphism, as we just got done seeing, of the complex points of X sub 1 of N to itself. Okay. But of course, I can also think of it as an automorphism on the S complex points of X sub 1 of N to itself. Okay, so we just got done discussing this upper map. It exists, it's an automorphism. Okay. We also already know what these vertical maps are, because we already know that X sub 1 of N, its complex points are an isomorphism with the complex points of S sub 1 of N. And I'll restrict that isomorphism to the S complex points of X sub 1 of N, and I get this vertical map. Again, what is the map? It just sends like an X here to the equivalence class of elliptic curves E sub X, P sub X, right? Where E sub X and P sub X are the reductions of E and P mod X. We've talked about this map before. So the question is there a map? Again, is there a map on the bottom that actually commutes the square? In other words, can I think of the diamond automorphisms moduli theoretically? Yes, you can, and you get a super simple, very easy to understand map. Here it is. You just send the equivalence class of the enhanced elliptic curve for gamma sub 1 of N, E comma P, to the equivalence class of the enhanced elliptic curve E comma DP. That's all you do. And DP here just means P plus P plus P plus P, blah, 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 D times. Remember, E is an elliptic curve. It's an abelian group. So you can add P to itself D times for sure. That's all it is. So the diamond operator takes an enhanced elliptic curve equipped with an N torsion point, P, and it just sends it to the class of E dP. That's all it does. Okay, so very clean as promised. How about the orbit perspective? What do diamond operators look like from the congruence subgroup perspective? There's also a commutative diagram as follows. Again, I already know the diamond operators, diamond of D, they're automorphisms of the complex points of x sub 1 of n. So that's what this upper map is. I already know that the complex points of x sub 1 of n are isomorphic to the orbit space of the action of gamma sub 1 of n on H star. That's what these vertical maps are. It's that isomorphism we've known about for several videos now. Again, the question is there a map on the bottom meeting the square? Or in other words, is there a way of thinking of the diamond operator orbit theoretically? What does it do on fundamental domains for gamma sub 1 of n, basically? Very simple map this time around. It wasn't super nice maybe for the Hecke correspondence, but for the diamond correspondences, for the diamond automorphism, it is. The map on the bottom here takes the orbit of Z in H star, and it just sends it to the orbit of diamond DZ. Remember, diamond D is a matrix. Matrices act on points in the upper half plane. They give us other points in the upper half plane. Diamond D times Z is just some point in the upper half plane. Okay, so I'm just sending the orbit of Z to the orbit of diamond D acting on Z. Okay, the proof of all this is in CSS chapter 3. And so, yeah, so thanks for watching, and I'll see you next video.